make our guests wait too long. Brian, thank you for coming. I've known Brian for quite a long time. And when he said he was going to be in the area, I said, okay, why don't you come and give us a talk? And so thank you for coming. I'm going to let you introduce yourself because you'll do a better job than I do. And then we'll listen to your interesting talk afterwards.
Great. Thank you, Khan. It's an honor to be here. Maybe I should start with some sort of joke. I'm originally from Korea, and someone told me that Korean food in New York City is much better than any food in Korea, because they actually import it to the US and they make it better for everyone in the world to be tasty. And I had a lunch at the Bukchangdong Sundubu. I don't know if you guys have ever been there. It's a really great and spicy food. Since I need to introduce myself a little bit, I got my PhD from Texas A&M a while back, and then I started my career as a research fellow at the National Statistical Sciences. So it's basically applying statistics for better use in transportation modeling process. So my big career has been focusing on simulation, model, calibration, and validation. And obviously, when you get a faculty position, you have to do something else, and been doing many other things. Some of the work I'm presenting today is related to the traffic signal is one thing, and the other is when we have a low market penetration of connected vehicle, connected automated vehicle, how can we actually take advantage of it? And hopefully you like the presentation. Some of the sponsors, I recognize NSF, and Virginia actually started with the Commonwealth Cyber Initiative, putting money into autonomous systems and cybersecurity side. Toyota Infotech is a group actually working for Toyota and then doing outreach of research. And Smartly is a regional center that UVA is a part of. And then Virginia Transportation Research Council is research division of Virginia DOT. They are on ground with the University of Virginia. I want to start with the video, see if you can enjoy this. I know some of you actually have seen it. So this is a video taken by movie director by timing closely to very tens of seconds of the detail, try to show what future will look like. Again, I did not make this video. Somebody actually shared with me. This is a often great way of starting the presentation, like this one. The automated vehicle concept started a very long time ago. This was in 1925, and people were thinking about how we can come up with the autonomous vehicle. And this was sort of dreamed of. Someday we might be enjoying playing game in the car drives itself. And we are, as you know, getting there. That's sort of what I want to show. A little bit of a history about this automated vehicle or autonomous vehicle. This research was funded by DARPA, and also Carnegie Mellon University started doing this no hands across America idea. So basically, they have a preceding vehicle following based on sensors, and the remote operator is actually controlling the acceleration, deceleration. The car follows the vehicle, and they did almost 98.2% across the 3100. That was sort of a remark that they've done by human, sort of part of autonomous vehicle driving. Real history, some of you might know, is Congress mandated this in early 2000 that because of a military engagement, they need to have some vehicle autonomously driving and getting our injured soldiers bring out to our home base. And they mandate that U.S. Military should have ground vehicles to be unmanned by 2015. So because of this, DARPA, as you know, the Department of Defense, need to have a ways of getting this done. So they announced something called the DARPA Grand Challenge, giving out $2 million, whoever actually can do this. Very first challenge, not many cars made it through. It was only given 7.32 miles getting through, but second, third year, actually they did it through real urban-like environment. You can probably watch videos from YouTube and other places. They were given literally one YouTube stick, and then you plug into car, and car has to do everything, including stop the vehicle blocking roadway and recognize that and backing up and weave through the area with the urbanized areas. And with this, you probably know Google actually hired or recruited Chris Armstrong to lead the division of Google driverless car, now known as Waymo. Google, as you probably know about this a little bit, this is a car from Toyota Prius. It's probably about $30,000. And when they were doing this, the LiDAR sensor they are using on top here was about twice as much as the vehicle itself. So that LiDAR can see pretty much everything. It's coming from military application, obviously. Velodyne actually developed it, and it's getting cheaper. It started with 128 channels, and researchers are using lower number of channels as well. But still, this is not affordable. But that's the history. How reliable these driverless cars, as you can tell, this is something called the disengagement report. As you know, if you are doing the autonomous vehicle testing, they have to actually get a license, and Caltrans requested that if you have a safety driver and how many times you have to take over, so disengaging the report. And when 2018 data came out, it was about 10,000 miles. So every 10,000 miles driven, there's a one incident of oops moment for human drivers. Waymo actually had one. In 2020, it went up to about 30,000. So Waymo and Cruise by the General Motors are doing pretty well, and AutoX and others are doing reasonably well, because if I drive 10,000 miles per year, I have at least one or two oops moments, and some of you probably do. So they seem to be doing better. One thing about data duped, some of the car manufacturers are driving only highways, try to add more miles added up to show theirs is doing better. Because in California, you have to do a lot of challenging urban environment, and so you have to be careful about whatever data you see, but roughly this is what you get.
For that,
Oh yeah.
how serious of like mistake is it? Is it like an accident, like they actually like crash, or is it just maybe they?
This one specifically disengagement. You have seen the Google driver this car had accident, and worse, Cruise actually made a scene in the California, right? But they are doing the Uber type rider sharing. They are not knowing about police cars, policemen's indications, and so there's a lot of errors. My former student actually works at the Cruise, and he texted me that he did a red light run, so it's not perfect yet, kind of thing. So there could be serious problems. You might have seen the Tesla being not paying attention to it. It's still so-called level 3, but they kind of over-trusted their car. So it's not perfect. Yes?
Wait, did you say Tesla's level 3?
Autopilot is considered to be level 3, yes. I'll probably show you that one slide indicating that it's not working. I need a tech person. Full battery, but not going to the next one. Oh, thank you.
This one's not working,
Takes time, I guess. I have to be patient. And then I want to give you just a little bit of a history on the connected vehicles. Some of you may know already. Back in 1999, US DOT, in the name of safety, we need to reserve this wireless bandwidth for transportation use. And this 75 megahertz domain bandwidth at 5.9 gigahertz seems like a trivial one, but if Verizon or T-Mobile wanted to buy this bandwidth, they have to pay over billions of dollars to get the bandwidth reserved. So hCCC agreed to reserve this bandwidth back in 1999. And over 20 some years, transportation society tried different things. We never really deployed this thing. Guess what happened? Wi-Fi groups and other communities wanted to use a portion of this area for newer Wi-Fi versions. So we lost some portion of the area of 75 megahertz. And now we are moving into also so-called the cellular V2X. This is a sort of expected because they started with a dedicated short-range communication, which is basically Wi-Fi version, which is free. And for Qualcomm and other companies, if entire transportation is using Wi-Fi based approach, they could not really sell chips and data. And they kind of lobbying into the cellular V2X is a probably better choice because Wi-Fi cannot be everywhere. You gotta have Wi-Fi connected somewhere. We don't have Wi-Fi everywhere. So having cellular V2X, we provide a vehicle to everything communication everywhere. And with the cellular, you still have a communication almost everywhere with the cellular data connections. So we are now moving into C-V2X era, and then US DOT just announced last October that they have a plan to accelerate V2X deployment. So we are getting serious about this connected vehicle environment. And most of the cars sold in the US right now actually have at least LTE 5G connections. And if you have a new vehicle from GM or Hyundai or Toyota, Honda, they all have connectivity. So it's a sort of connected vehicles. This is a sort of a projection. How soon can we have a fully connected and automated vehicles? There are several different market research firms that are doing this. But the bottom line is ideal case of sales. Sales is the highest. Typically in the US, 3% of cars are new vehicles. Even with the 3% of new cars are all equipped with the CAV, it's taking very long time to get to close to 100%. So we'll have to live with partial connected and automated vehicles. So that's the point of this control environment. So what can we do when we have a small market penetration rate? People say they want application as a transitional priority. It's true because only buses are connected and possibly automated vehicle, and then signal communicating with that intersection is connectivity have them, then you can actually do the transitional priority with the connected vehicles. So when US DOT wanted to do this connected vehicle deployment, TSP has been sort of day one application to be recognized as day one applications. So I'm going to show how we can take advantage of TSP with the connected vehicle environment. And then adaptive cruise control, more than half of the newer cars actually equipped with the hCCC. Even for Toyota, low-end vehicle has actually hCCC capability, which is very convenient for stop-and-go traffic, especially in New York City. There are some challenges, and sometimes a driver wanted to be in charge of their acceleration and decelerations. And can we do better than hCCC is another idea that I'm going to share. And as you know, the automated vehicles, Waymo, Cruise are the leaders of doing that. And Tesla just announced the version 12. I don't know, have you read about the newer version? It's much better than previous ones. One of the reasons is that before version 12, they actually used extreme cases of impending crashes and crashes. They trained those to avoid. Then they realized that it's just too many of them. Estimated is 10 billion crashes are out there in the record, and how can you actually train them all? They decide to train good driver behavior. So they scratch everything out, build from the bottom up to have a good driving behaviors, and they seem doing a lot better. And OpenPilot, I don't know how many of you heard of Comma AI. It's a low end of the open source community. It actually works pretty well with the newer vehicle. About 200 plus vehicle actually can take advantage of this Comma AI's OpenPilot autonomous driving kind of behavior, it kind of works as well. It's coming up. What are the issues of TSP that we have out there right now? TSP is a good way of promoting the multimodal operations. When bus is behind the schedule, and the worst case happening is a bus bunching together. So behind and another same bus is going together is the worst case. So how can we actually allow a bus behind the schedule can take advantage of the going through intersection, and we cannot really treat that bus as an emergency vehicle. It has to be somewhat passive way of getting greens. So somewhat limited in terms of providing green for bus. So you are near end of the green, you extend the green to get bus pass through the intersection, or you are a few seconds before the green bus is coming, you truncate the green from the other approach and then allow bus will go. So the window is very small, and can we actually do better than this? Most of the practical use of TSP simulation-wise showed a good benefit, but real field tests, they have some challenges. Some of the challenges, worst case is a bus getting extension of green, but somehow because of a queue ahead of it, you could not get through. And that's a worst case because you are adding more delay to cross streets, and the bus is not getting through. Sometimes it has a small benefit because of the window I mentioned. And then current technology doesn't have how to include accommodating the conflicting TSPs. So we have two major streets getting crossed together, and two bus request the TSP. They don't know which one to serve. They just serve whatever first come, first serve, which may not be the case. So a lot of challenges. If we can take advantage of this connect the vehicle, which we call it TSPCV, one of the true benefits of having connected vehicle is so-called the two-way communications, because the current TSP is one-way communication, just like the emergency vehicle preemption that you are doing. It's using technology, sending message to the signal. The signal receives it and look at the current signal setting, and once it meets the minimum greens and then pedestrian crossing time, that it allows for preemptions. But for TSP, it has to see whether you can extend the green or not in very small window. And there's no way to do so-called the cooperative control. And the biggest benefit to me having connected vehicle is you can do a lot better than automation by allowing cooperative control. You can actually coordinate together. And we are doing better real-time traffic information, accurate arrival time prediction based on sort of an average traffic flow. But if you have a more connected vehicles, your accuracy can be much, much better by knowing cars ahead of you and so forth. And then we can have them in a better control logic. So what we proposed to allow better than existing TSP, as I noted, the TSP happens only when bus arrives to at the close to the end of green, you extend the green 5 or possibly even 10 seconds, so bus can get through. Or bus is arriving close to the end of red, and you are truncating red of green from the other approach, and you give a bus to get the green. So window is very small. And what we figured out is that if we are really confident in estimating arrival time, we could actually move a portion of green to the location where bus arrival happens. And you need to make sure queue ahead of a bus is getting cleared, and that's a good estimation you can have. You might have known about queue polygon method of how many queues ahead of you, and have a very good estimate. That's what we do in the modeling side. So by reallocating, reallocation, we can actually have a bus is getting through entire cycle, not just a small window of beginning or ending of the green. So that's the new technology we introduced by having TSP with the connected vehicles. Hope that makes sense. I am not going to explain this in great detail, but this is basically minimizing total person delay. The argument is, if a bus is empty, even though it's behind the schedule, it's probably not a good idea to allow bus getting through. Maybe you have expected more passenger coming up, possibility. But we try to look at the entire person delay, including buses and passenger cars. And we are looking at over n cycles. And in this case, we decided to do 3 cycles ahead of time, see if we can make it work. And all the constraints, and then we allow where bus can actually do grid reallocation or just simply getting through during the grid, that's best. You don't have to do anything. I have not shown details about when there's a conflicting movements. When 2 buses are conflicting each other, we can actually compete those evaluations with the 2, which one giving top priority allows a lower minimizing total person delay. If there's a 3, we solve it by 3 combination problems and so forth, and then we can do them easily. I'm going to just show how we evaluate it. We have a base case without TSP and conventional TSP, and then TSP with the connected vehicles, looking at the bus delay. So we are going to improve bus travel time and the person delay of all vehicles. And then we use a real network, but data is all assumption with the different conditions, because we want to make sure different congestion level is considered. So that's how we did it. We did analytical modeling, which is based on optimization. We assume everything is average flow. We are also looking at the simulation based. Simulation will allow variations in arrivals of different vehicles, different delays. Even though you have average hourly flow, each cycle you have a different number of arrivals. So we are generating those and using VISM, and then this is a commuter base to work with. So this is a results based on analytical delay, which is we assume average flow. We are doing sort of a coupling method of the estimations. So it's mostly average behavior. And once we have a good behavior, if you have a good solution in the bus travel time and product delay minimization, good performance of the average also has a very small variability in stochastic environment. The good average has a small variation, really bad average or worse time has a really large variations. So that's why we kind of considered in the optimization. You can see bus delay is improved even close to 1.0, volume to capacity ratio approach, delay per person improved. And this is one important understanding of why this would work. If you look at the bars on the top higher one, this is an actual bus delay, bus travel time. If a bus arrives at the beginning of a red, they wait very long time. And if they arrive beginning of green, they just get through. And we want to make sure that bus will be able to get through this bottom shaded area. That's how we got out of the TSPCV. If you are using conventional TSP, you are only allowing bus arriving beginning of red, so you are actually extending green 5 seconds and then bus will get through. Bus is arriving more than 5 or 10 seconds later, they cannot really get the bus priority. And this is again, you can save by truncating green from the other approach. So you're opening green earlier for bus to get, so bus will have a reduced delay. So what we are looking for is the bottom reddish chart. That's the actual performance of bus under TSPCV, which basically reallocating green times and then doing it. And then stochastic simulation also shows significant improvements in bus delay and person delay. There's a variation, so it gets worse, but it's not significantly different big changes. So overall, we can make it work. What I am currently doing most of the time is doing simulation done is not really good enough, even though we could not convince Department of Transportation or the Public Transit Agency to do this algorithm. We wanted to test to see if this works. So we actually worked with the Virginia Tech's smart roads. They are roads reserved for doing research, fairly long corridor area. We have actual traffic signal cabinet, signal heading, communication devices, algorithms we developed running in the laptop. So from the laptop, we actually calculate the bus arrival. We couldn't use the bus, we use passenger car, but acting as a bus. So we know the arrival times and we give that information to the signaler and signaler responds to it. And we actually test it out, see if this will work. That's kind of important for doing research. So this is the idea of allowing how we can actually do this with green reallocation. The dotted lines, if you see the green, the bus can get through, and bus is doing this, then they have to wait for a long time without having TSP. And you could again allow bus can get through by having the green extensions, but you cannot do that bus arriving there. In our algorithm, we can actually have a TSP green time to be inserted into here by reallocating green time. So overall amount of green time given to the approach is similar. Obviously, we lose yellow and red clearance time because every time you change it from green to another green, you have to introduce that yellow and red clearance time. Other than that, bus can actually get throughout the entire cycle. That's important. So this is a sort of results we are doing. So one of the challenges is GPS errors of the bus. So bus has a AVL, automated vehicle location system, and GPS errors are oftentimes higher than ocumeters. Most of the time, you cannot really recognize which lane a vehicle is on. Is one challenge. We tested out these. So bottom line is column here, number of TSP green phase with the shorter delay without green extensions is what we wanted to see. And then we are also looking at the percentage of those. And most of the time, by having better differential GPS, will have very accurate GPS information. You can do a lot better. But at least in the scenario, we assume the prediction of typical vehicles ahead of it is known. So we can actually make it through the getting through. So it's pretty decent results, and they show that it's working. Any questions about this? TSP? Yes.
I'm just curious, so when you talk, there are like two buses. Are you considering two buses coming from different approach, or it's more like bus bunching from the same approach?
We were looking at the conflicting approaches. So the ideal case is the bus is coming from both ways, and they could go through during same green. Worst case is a bus coming from diagonal. So in that case, we are optimizing total person delay by looking at the two buses scenario for 3 cycles ahead of time. We had a series of the work. I'm just showing the simple case, but another paper we did was bus has to have a progression along the corridor, and when they have a coordinated system. When you have a coordinated system, one of the pitfalls is early return to green will interrupt your progressions. And bus will happen that as well. So we are actually making sure that bus goes to the next signal, it still gets the priority of the bandwidth. So we have a series of papers working on. So you can consider.
Yeah, that's interesting. And also, I'm asking just because specifically in New York City, like a very congested urban area like New York City, you might see multiple buses coming at the same time, even during the same approach. So I'm just curious, like maybe in the future, that can be some scenario to be considered as well.
Yeah, I mean, we were thinking about doing 3-4 buses together. Then we realized that we can just run multiple times over 2 buses cases, and then evaluate and then go for. That's how we did it. Because doing more is more complicated and taking longer to solve.
That's true.
Yes.
This is probably difficult to quantify at this point in time, but what is the driver perception that if you have a signal which normally has your 90 or 120-second signal length, and you get a 30-second cycle and then a 40-second cycle back to the 120, does that alter public perception, and in what ways does that public perception affect the ability for public transportation?
Excellent question. Honestly, we did not consider, but most of the drivers, they see maxed out green, which just goes into the yellow any given time. They are not expecting, unless you have a countdown of signals. So depending on the length of the link, but they are probably not recognizing this is short. We guarantee minimum greens and those pedestrian greens, so we are doing outside of those. But that's an excellent question. Yes?
Excuse me, does this changing signal occurs locally on just one intersection, or you are considering the change of the signal timing on a network?
Yeah, we actually start with the single intersection, but as I mentioned, the corridor has a progression bandwidth. And then this will interrupt that progression of bus. So we have another research paper looking into the progression to the next intersection where buses are moving. So we are doing sort of a local optimization. We are not looking at the entire corridor, how buses should be moving together. Because this is a local problem. So we want to make sure that existing TSPs are doing very short duration of extending green or truncating green from the other approach. That window, we are doing entire cycle. We want to make sure that bus will get green by using green reallocation. And once they get it, and their bus is not on the bandwidth of the corridor, and we actually extend that coordination to the next signal. That's how we sort. And obviously, there's a different solution if you look at the entire network. Okay, those are excellent questions. So this is a US DOT's definition about ADAS versus ADS. And their definition, ADAS is a level 2. That's probably, and then it's interesting, DOT decided not to use a level 2, level 3 anymore, but the public never understand what it means. So they are trying to talk about advanced driver assistance systems and automated driving systems. And obviously different levels of it. And ADAS is, I can run video, but this is a lane keep assistant system. And if you have one, it's really convenient. It's avoiding you from getting the other lane. It kind of forces your steering wheel coming back, unless you have a turn signal on. It's great. And second is obviously adaptive cruise control that I'm going to explain why we are focusing on this research area. Video runs, I guess. This is how you can see them. Has anyone actually used hCCC a lot of times? Are you happy with the hCCC most of the time, or?
When I want it, it's great.
Okay. Did you have any case that you didn't like it?
I was driving in a caravan with friends, and my friend behind me also had it, and I realized that I could adjust my speed to have theirs like disengage, and so I could start to like mess with them.
Okay, so for the accordion effect is a different thing, right? Okay. Anyone else? Okay. So hCCC is great for adjusting speed based on sensing to the preceding vehicle, and you have actually different sensing, one vehicle distance, 2 or 3 vehicles. It works great in most of the time, but when the preceding vehicle changes the lane, and you have a huge spacing, and most of current hCCC accelerate to catch up with another target vehicle to have that distance. And people don't like that. It's kind of scary, just accelerating so rapidly. Another issue is when the sharp curve area, it is not really doing dynamic adjustment of the sensing. It's just looking at a different one and accelerate. It's scary as well. And these will be updated and then could be better. They are actually looking into typical driver acceleration behavior and then try to use that behavior when the preceding vehicle changes the lane. But without thinking that, it's just doing the huge accelerations. And because of that, people just cut it off. And then also, drivers often wanted to be in control of doing acceleration and deceleration. I want to be in control, like if people wanted to drive a manual transmissions. How many of you actually know how to drive manual transmissions? That happens. So human as a driver, and they want to have smooth driving, not dangerous situations. This is one example showing perception reaction time as an x-axis. So your perception reaction time, even you are very well alerted, it's at least 0.56 seconds. And without inattention, you go 1 point some seconds or 2 seconds. That's where you might have crash potentials. And then TH is a time headway to the preceding vehicle. So in general, human has to have at least about 1.2 second-ish time headway to be comfortable, depending on speed, obviously. And then the reaction time should be less than about 0.6 seconds to be able to respond to whatever is happening to preceding vehicle. So this white area is something we call string stable, smooth following behaviors. And we want to make sure this can be extended for other cases is what we're trying to do here. And you might have seen this chart. This is borrowed from the PTV psychophysical car following model. So human as a ego vehicle as a human driver following preceding vehicle with the spacing. And that's sort of where you are here. I know it's not shown up to the people on the Zoom, but you have delta x being very positive, and your speed as a huge spacing, you are higher speed than preceding vehicle, try to catch up. So your delta v is positive. And when you actually maintain that higher speed, you are going down to narrowing down the distance. And you are continuously doing that. Some point you feel like dangerous. I'm getting too close. What you apply brake. And your delta v is smaller and smaller. Sometimes you are slower than the preceding v. Then what you have to speed up again. So this is sort of a circulating. While doing that, human is probably doing too much acceleration or too little acceleration, or too much braking or too little. And that's in reality. And can we actually do better than this is the research motivation. So we want to take advantage of connectivity. So if a human-driven ego vehicle is following connected or connected automated vehicles, instead of doing hCCC, because it's not doing very well for some cases, if I'm in charge, I'm often doing too little, too much acceleration, decelerations. And if I can get something called the signal from the preceding vehicle, intended acceleration, deceleration through the communications. And I can take that into the consideration and develop adjustment of the human acceleration. So human is put the gas pedal on, then immediately want it to go fast. And we are adjusting its acceleration in an optimal way to be string stable. String stable means that you have a smooth flow, and that saves the fuel consumption and everything. So that's what we have in the algorithm. So this is a sort of a math behind it. Again, if you are really interested and happy to discuss in detail, in a nutshell, we have a transfer function to looking at the string stability, and we want to adjust the automatic portion of this G function based on what human does, based on simple OVM model, which is a very simple coupling behavior, what human intentions are. And then by applying G function, we are creating this human behavior to be string stable or optimal acceleration decelerations. It's a fairly simple algorithm. You might have a question about how to identify connect the preceding vehicle, because when we do the even cooperative adaptive cruise control or doing this hCCC, we call it human in the loop connected and cruise control, what we are doing, we have to know which vehicle is sending which acceleration as a feedforward signal, because in reality, there's more cars sending the signals. A lot of connected vehicles. You don't want to follow a vehicle, this vehicle's feedforward signal. You have to follow that vehicle that you know you are following. Or sometimes you don't know which one is sending. You shouldn't be following the preceding vehicle because it's not connected vehicle. So that's a very important, simple, but a lot of researchers assume that's a given. In reality, they are not, because the basic safety message based on the CV2X or DSRC, they are simply sending their location information with the GPS, acceleration, deceleration, a few others information. They are not allowed to send any personal information. If we can share a license plate, color of vehicle, that's great, but we're not allowed to do that. So it has to be figured out by an algorithm. So that's where we are doing research. We figured that this can be done by matching with a nearby vehicle, knowing they have errors in GPS, and then knowing there's a reasonable sensing of the distance measure based on radar sensor or even the time of flight sensors. So we are doing that. And then this is optimization. It's not a simple matching, it's a literally done optimization. What is the most important part is we don't want to follow unconnected vehicle as a connected vehicle and then start doing this hCCC or even CACC, cooperative electric cruise control, because this will have a possible crash. So we are putting this into a hard constraint. 10 to the minus 8 is a very small number. We want to make sure that errors are less than that. And then we want to also minimize the two things. One is, it's not worst, but it's not good when we actually, knowing this is, truth is that this is a connected vehicle, we identify as an unconnected vehicle. So we are not following, which is not the worst, but it's not good. So we want to minimize that. And also we want to minimize this matching process of a consistency check. When can you declare with the less than 10 to the minus 8 error, this is the connected vehicle we need to follow. So it's basically doing the time consumption minimization. So it's a very complicated optimization, but it's doable. That's how we did it. And again, we want to do the field test. Make sure that this will work in the real world. And then so sort of potential with the commercialization idea, we want to have a prototype, affordable, again, proof of concept, and do some showcase of technology, and then looking for commercial product development or possibly licensing opportunity with the OEMs. So we actually have NVIDIA Jetson Nano, which is probably arguably better than Raspberry Pi, but it has a GPU in it, faster, and then it can do machine learning as well. And we use the Wi-Fi dongle in part because it's affordable. We were not able to actually purchase the CV2X. We did a test with the DSRC, the original version of the communications. It was not a mass production. We had to pay a few $1,000s to get that roadside unit and then onboard units, which was outdated anyway. It's all based on Wi-Fi anyway. So we decided to just use a simple Wi-Fi dongle you can get probably $10 from the Amazon. And then third is a sensor. It's called a time of flight sensor. Again, this is cheaper than using radar or LiDAR. Radars are over $1,000. LiDARs are at least $10K, $20K. Time of flight sensor is a very affordable, short distance. It goes about 60 meters. It can go a little bit longer, but we use this one. It's about $150. And then GPS receiver. This was a challenge. We thought every GPS can do 10th of seconds, 1.1 seconds update. Their default is 1 second. So we had to buy multiple of this GPS. And this one's not cheap, but it's actually doing 10 hertz. So we were able to actually measure them. And then typically it has a 2.5 meter error, just like a regular GPS in your phone and others. So idea is having 3 vehicles running and testing out and then do the thing. We were able to do it only 2 vehicles, but this is what we did. For safety, we are using the parking lot and then Evo vehicle, preceding vehicle running. We had to run the optimization with the assumptions. What is the assumption we had to use? The bottom bullet. We used the type of sensor error is very small, 0.1 meter. GPS error is about 2.5 meters standard deviation. So that's the assumption we used. And then with that optimization, we are able to do the parameters. I mentioned about 3 optimizations. So with that, we were able to run it. Here's the most interesting part I want to make sure is that the communication latency. The communication latency of a Wi-Fi is known to be lengthy. Your Wi-Fi requires sort of handshake, authentication process. We don't need that in this case for the testing. So what's showing that this is like a communication error was a 0.0055 seconds, which is literally almost 0. Because our DSRC CV2X is doing communication every 50 milliseconds. So as long as we communicate and receive that data to calculate, we should be okay. So that was the really happiest moment to know the latency is very small, and we actually had over 2,600 pairs of GPS sensor data, because each testing requires multiple checks, potentially having the errors and consistency check and so forth. With the 43 tests we have conducted, 100% accuracy was good. Obviously, it's only 2 vehicles, so there's no errors. But still, we want to make sure that this prototype can work with the real-world environment. It seems working pretty well. So with this, if we can actually do that, improve the human smooth driving with this technology, it can be anywhere on the human perception reaction time, as long as we maintain certain time headway. And if you shorten the time headway, there might be some oscillations. Even adaptive cruise control is not string stable. The definition of a string stable comes from mechanical engineering. What they define is that following or ego vehicle should be able to follow smoothly the preceding vehicle without going over its speed, without going down too much into speed, lower than current speed. So it's just maintaining smooth stream. And we were able to do that with 1.15 seconds or ish. hCCC requires over 2 seconds to be string stable, depending on how good the car is. But so that's a big difference. So we actually tested out this. The third bullet is the key message. Help the human driver achieve smooth driving on speed and acceleration. So we actually looking at the human accelerate, decelerate based on comfortable spacing, the human sees. And then we are operating this to be string stable. This is a very cheap driving simulator we have. 8 driving experiments. hCCC can reduce oscillation of acceleration by almost 36%, time gap 81%. Most importantly, with the smooth acceleration, the pure saving can be up to 15.8%. I have a small video running the difference. So top is without assistance. It allows the driver trying to follow up, accelerate, decelerate all the time. And the results are shown on the right-hand side. The speed trajectory of a human without being trained is lousy following the preceding vehicle. But if you actually use our hCCC, it gets really close. And notice that ego vehicle is be able to do preceding vehicle without over going to their speed. So that's a string stable conditions. So that's the key we have developed. So the take-home messages are, the first, connect the vehicle technology with the TSP can actually improve its operations. It's a breakthrough. We are starting a small project with part of the UTC and working with the industry partner. Hopefully we can demonstrate this in the real world again and then use for doing better TSP. The more cars are connected, the possibility to be connected, and having the roadside unit at the signal is not that expensive. So we're trying to look at that. The next vehicle identification system that we developed, this is something, a must. You cannot really assume cars can communicate with the other vehicle immediately, because they cannot. If we want to know what they are doing, all you are getting is a broadcast message. With accuracy is not good enough to know this is a car A, B, C on the lanes. So having this connected vehicle identification system, we'll be able to have a very good way of identifying them. And so that will help not only doing this hCCC, it can be useful for doing cooperative adaptive cruise control or even merge behavior, freeway merge, or even lane change. If you have a platoon of CACC, if you need to allow another CACC joining in between, or vehicle leaving from that, and you have to communicate them. You might have seen video of a real world vehicle doing cooperative adaptive cruise control. When they do, they actually have a hard-coded vehicle number. So when the broadcast of the vehicle information is given, they know exactly, I am the number 4 vehicle, which vehicle is sending the information. That's not going to happen in real world because you cannot pre-assign those numbers. And you also have a Toyota, Yaris, Hyundai, Ford, and other vehicles. They might have a slightly different way of doing the communications. Human in the loop connected cruise control is, we think it's an innovative technology, improving existing adaptive cruise control by taking advantage of connectivity, even with the low market penetration rate. So that's sort of 3 take-home messages. That's pretty much it, I guess. This is, I have not. Oh, this is a slide without my students' faces, sorry. But these are the recognizing the sponsors and small students. I thought I added in, but I forgot to add. The small students actually work on this project, which really appreciate their help. Wanted to leave a good amount of time for questions. That's why I rushed through. Yes.
So my question is, so you mentioned the negative vehicle identification. So from my understanding, it's like the objective of this algorithm is to identify the preceding vehicle is connected over to the vehicle. So my question is, so it's, you mentioned it's achieve 100% success of identification experiments, but my question is like, so what traffic condition is experiment? I'm thinking like if the traffic density, like if so many traffic conditions and traffic density or any other stuff to affect the performance.
Right, it's not guaranteed, but the way the algorithm is developed is based on the error distribution. So we assume the time of flight sensor has normal distribution with the 0.1 meter errors, so standard deviation, and then GPS having 2.5 meters. Some of the GPS devices argue they are 1.0. And we actually measured these, and then they are fairly close. So if we know real world dense environment, what are the errors from the samples? And we can adjust these parameters. So we assure the minimum error that we misidentify unconnected figure as connected is less than 10 to the minus 8. And arguably, there's a million vehicles having 10 to the minus 8 is a very big number. But we don't engage in doing hCCC all the time. So we can correct them as we go. But we can change if that's something critical. But that's a sort of a beauty of doing algorithm development and then testing. So that's a good question.
So my second question is, like, would that identification error rate change with like the market penetration rate and also traffic conditions theoretically? Like, would that be like, so is it possible like we can find a relationship?
Yeah, that's how we did it. I'm not an expert in GPS, and they are trying to deploy something that can do centimeter level GPS accuracy. If that happens, they don't need our algorithm. But right now, if you are using your cell phones or other things without differential GPS, it's literally impossible to know which way you are at. So that's a challenging part. The good news about GPS, even though location is not accurate, the speed of GPS is very accurate. There's changes. So we actually advanced our algorithm by adding, not only looking at the distance difference based on the two GPS locations, we are looking at the speed difference as well. And that actually improved our algorithm without actually improving GPS accuracy. So there might be different ways of doing that. And obviously, centimeter level GPS accuracy, you're good to go.
So my third question is like about, you mentioned like this hCCC decrease the time of the vehicle exposed to the unsafe scenarios by 85%?
The differential in the acceleration, oscillations, and other things. Yeah, I can go back and check the numbers. So it's basically doing string stability, which means that you don't have to do spike in the acceleration. And the human actually does that, right? Human is not aggressive. They actually have a very high speed than preceding vehicle, and then they get too close. They have a really harsh braking to maintain safe distance. So that's not good for pure savings, right? Pure consumption. So ours is actually assuring you don't go beyond the needed acceleration or deceleration by adjusting the human's intention based on what preceding vehicle does in terms of their accelerations.
So I'm curious, like, what's a standard of criteria to define unsafe scenario?
So our case, we are looking at the desired spacing. So if you actually maintain, you want to have there's a different way of looking at it. Time headway is given, like a 1.2 second headway is my safety distance, and then sometimes it violates, right? And then if it's a positively violates, then it's dangerous. Negatively, it's safe. So we can actually look at those. The spacing error is what we are looking at as a surrogate safety measure. Does that make sense?
Yes.
Yes.
Is the process of designing your cruise control algorithms, is that how the actual OEMs think about how they design their algorithms? Is that something that they are looking to adopt? what is the process of getting these into the actual vehicles on the road?
Excellent question. OEMs never share how they do their hCCC. I mentioned about Comma AI. So Comma AI is open source, community-based development. We are starting a project doing this hCCC using Comma AI. Comma AI device, anyone heard of actually using Comma AI? Okay. Right now it's a 1250 device, and then you actually have a really high-end CPU and Wi-Fi connectivity, and using stereo cameras, and then another camera looking at the driver's face, and it actually implements autonomous driving, ADS driving level. And we are using that technology to get information from the immediate preceding vehicle and try to adjust the acceleration. We have not figured out all the details, but that's a project we are trying to do. With that, I'm hoping OEMs are willing to adopt our technology, possibly licensing or even just taking advantage of what's out there is a plan. We've been talking to OEMs. They're not really open to, I mean, Toyota even funded us doing the similar research. And what's happening in Japan versus what's happening in San Francisco, there's some gaps. But they seem interested in. They said in Japan, at least 2% of cars are already connected, and they wanted to look at it. And Volkswagen in Europe, they're also looking into this, how to take advantage of connectivity. So we are into right direction. Great.
So if you know the question, thank you, Brian, for agreeing.
Thank you very much for your attention. We appreciate it.